Hello everyone, welcome back to SHR Trinity. In today's video, we are continuing our machine learning interview question series. This is part 3, where we will dive deep into data preparation and model evaluation, covering questions 21 to 30. Building robust machine learning models requires meticulous cleaning, formatting, and careful metric evaluation. Let's study these essential topics in detail. Before we dive into the questions, let's look at what we'll be covering in this video. We will discuss data preparation and model evaluation. We'll learn about data preprocessing, handling missing values, feature scaling, normalization versus standardization, one-hot encoding, feature engineering, cross-validation, confusion matrices, precision, recall, F1, score, and ROC curves. Question 21. What is data preprocessing? In any data science project, raw real-world data is almost always messy, incomplete, inconsistent, and filled with noise. If you feed this raw data directly into a machine learning algorithm, you will get poor results, a concept famously summarized as garbage in, garbage out. Data preprocessing is the systematic phase where we clean, transform, and structure this raw data into a clean format suitable for models. The preprocessing pipeline consists of 4 major steps. First, data cleaning, where we resolve missing values, smooth out noise, identify and handle outliers, and remove duplicate rows. Second, data integration, which combines data from multiple sources like databases or files into a single unified dataset. Third, data transformation, which includes scaling numeric features, encoding text categories, and engineering new inputs. Fourth, data reduction, which simplifies the dataset by removing redundant or highly correlated features to make training faster and prevent overfitting. Question 22. How do you handle missing values? Missing data is an inevitable problem in real datasets. If we ignore missing values, standard machine learning libraries will throw compilation errors. We have 3 main strategies to handle them. The first is deletion, where we drop the rows or columns containing missing variables. This should only be done if the missing portion is very small, say under 5%, and is missing completely at random, otherwise, dropping data can introduce severe bias. The second is imputation, where we fill in the blanks using statistical measures. For numerical columns, we replace missing values with the mean, or preferably the median, which is robust to outliers. For categorical columns, we impute the mode, representing the most frequent category. The third is advanced imputation, where we use algorithms like k-nearest neighbors imputer or mice to predict the missing values based on other features in that row. Look at the code on screen. We use pandas to read a CSV file, fill missing age values with the column median using fillna, and drop rows that are missing the salary target using dropna. Question 23. What is feature scaling? Feature scaling is a preprocessing step applied to independent numerical variables to bring them into a common range. Let's look at why this is essential. Imagine a dataset where the feature age ranges from 0 to 100, and salary ranges from 0 to 100,000. If we calculate the distance between 2 points, the salary differences will completely dominate the calculation simply because of their units of measurement. Distance-based algorithms like k-nearest neighbors, support vector machines, and k-means clustering are highly sensitive to this and will ignore the age feature. Furthermore, for algorithms optimized using gradient descent, such as linear regression, logistic regression, and neural networks, having features on completely different scales causes the loss function contour to become highly elongated, making gradient descent oscillate and take much longer to converge. Feature scaling resolves both problems by standardizing the range of all numerical inputs. Question 24. Normalization versus standardization. Look at the comparison table on screen. Normalization, also known as min-max scaling, shifts and rescales the data so that all values fit precisely between 0 and 1. The formula subtracts the minimum value and divides by the range. However, normalization is highly sensitive to outliers. If you have an extreme outlier, it will squash all the normal data points into a tiny, indistinguishable cluster. It is best used when the data distributions do not follow a bell curve, such as in neural networks and image processing where pixel values must reside between 0 and 1. Standardization, or z-score scaling, centers the data around a mean of 0 with a standard deviation of 1. It subtracts the mean and divides by the standard deviation. Because there are no bounding limits, standardization is far more robust to outliers and preserves the distribution shape, making it the preferred choice for algorithms like PCA, support vector machines, and linear regression. Question 25. What is one-hot encoding? Most machine learning models are mathematical systems that can only perform calculations on numerical values, not text strings. Therefore, we must convert categorical features into numbers. If we simply assign a number to each category, like red equals 1, blue equals 2, and green equals 3, the model will assume a mathematical relationship, implying that green is greater than red, or that the average of red and green is blue. To prevent this, we use one-hot encoding. This technique creates a new binary column for each unique category, representing the presence of that category with a 1 and absence with a 0. To avoid the dummy variable trap, where columns are perfectly correlated and cause multicollinearity, we drop one of the encoded columns. Look at the code. We define a simple data frame with red, blue, and green colors, and apply PD get underscore dummies with drop underscore first set to true, creating color underscore green and color underscore red columns. Question 26. What is feature engineering? Feature engineering is the process of transforming raw data features to better represent the underlying problem to the predictive model, thereby boosting its accuracy. It is often described as the most critical and creative phase of a data science project. Instead of simply feeding raw columns into a model, we use domain knowledge to construct new variables. For example, a raw timestamp like June 14, 2026 is difficult for an algorithm to learn from directly. However, by extracting features like hour of the day of the week, holiday status, or fiscal quarter, we provide highly informative signals. Similarly, combining height and weight to create body mass index helps the model capture nonlinear relationships. In practice, good features are what separate mediocre models from winning models, often mattering far more than hyperparameter tuning. Question 27. What is cross-validation? If we evaluate our model's performance on just a single train test split, the score can be misleading. We might get lucky and get a high score simply because the test set was exceptionally easy, or get unlucky with a difficult split. Cross-validation is a statistical method used to obtain a much more stable and reliable estimate of model performance. The most common technique is k-fold cross-validation. The dataset is randomly divided into k equal-sized subsets, or folds. The model is trained and tested k times. In each iteration, one fold is held out as the test set, and the remaining k-1 folds are combined to train the model. This process rotates so that every single fold is used as the test set exactly once. Finally, we average the performance scores across all k iterations to get a robust, generalization score that accurately reflects how the model will perform on unseen data. Question 28. What is a confusion matrix? Look at the layout on screen. A confusion matrix is a highly detailed table used to evaluate the performance of a classification model. Rather than giving a single accuracy score, it breaks down the predictions into 4 key quadrants. True positives are positive cases that the model correctly predicted as positive. True negatives are negative cases correctly predicted as negative. False positives, also known as type 1 errors, are negative cases that the model incorrectly flagged as positive, creating a false alarm. False negatives, or type 2 errors, are positive cases that the model missed and incorrectly classified as negative. Analyzing this matrix is crucial, because in many real-world scenarios, the cost of a type 1 error is vastly different from a type 2 error, and this table helps us see exactly which mistakes our model is making. Question 29. Precision versus recall versus F1 score. Look at the comparison table. Relying on simple accuracy can be extremely dangerous if our classes are imbalanced. For instance, if 99% of transaction data is legitimate, a model that classifies everything as legitimate is 99% accurate, but completely useless at detecting fraud. Instead, we use precision, recall, and F1 score. Precision measures how many of the predicted positive cases were actually positive. It is our key metric when false positives are highly expensive, such as in email spam filters where we don't want to block important messages. Recall, or sensitivity, measures how many of the actual positive cases we succeeded in capturing. It is critical when false negatives are dangerous, such as in medical diagnoses where we absolutely cannot afford to miss a sick patient. The F1 score is the harmonic mean of precision and recall, providing a single balanced metric when you need to optimize both. Question 30. What is ROC curve and AUC? The receiver operating characteristic, or ROC curve, is a threshold-independent graphical plot that evaluates binary classification models. It is constructed by plotting the true positive rate, which is recall, on the y-axis against the false positive rate on the x-axis across every possible decision threshold from 0 to 1. The area under the curve, or AUC, calculates the total area beneath this plotted line. The AUC score ranges from 0.5, representing a completely random model no better than flipping a coin, to 1.0, which represents a perfect classifier that never makes a mistake. The key advantage of ROC-AUC is that it measures the model's overall capability to distinguish between positive and negative classes, regardless of the decision threshold chosen. It tells us how well the model ranks predictions, assigning higher probabilities to positive instances than to negative ones. Thank you for watching. If you found this video useful, please subscribe to SHR Trinity for more videos, and click the like and share buttons. Stay tuned for part 4, where we will cover advanced machine learning concepts. If you are interested in attending our live training sessions or have any inquiries, all our contact details are displayed right here on screen and are also available in the video description below. Feel free to reach out to us. We would love to have you as part of the SHR Trinity learning community.